try and get started soon. Yeah, sorry for the tight quarters. Normally we're in kitty, but this was kind of very hastily planned because of a break and other reviews going on in bigger rooms. So we're kind of smushed in here. SITTV is recording it, so the video is going to be posted some point, maybe tonight, maybe tomorrow, definitely before the test. And my laptop is somewhere with an Excel sheet for attendance. If you can put your name and email down, I'll send out the notes at some point tonight or early tomorrow, so that way you can review that. And I'll send out my tests from last year with all this stuff. The only difference is that last year we didn't have 4-year series, and I've heard the general consensus is it is on the test this year. So that's the only example that I'm not going to have strictly on my test, but all the others should parallel very closely. Okay. So just a couple of things. This is my email, so if anybody has any questions between now and Wednesday, you can send me an email, let me know. These are going to be the general topics that I cover. I'm pretty sure that covers everything. 4-year series, we're going to get to it at the end, and that we're only going to touch on a little bit because it's only like the beginning parts of 4-year series that are going to be on this test. So we'll worry about that when it gets to it. And then these numbers here are just the numbers on my test that correspond to those topics. So I'm going to be going over each example when we get to those sections, so we'll worry about that. And then this is just the Laplace transforms that we're going to be given to you on the test. So I just wrote them down at the beginning, so that way we can refer back to them for all the different steps that we're going to be doing. Okay. So I guess without further ado, we're going to start off with some Laplace transforms. So my name's Jake, by the way. I didn't say that. Hi. So we're going to start with the definition of Laplace transforms. So all the Laplace transform is it's going to give you a function in terms of t. You're going to convert it to something in terms of s, and then you're going to do some weird stuff, and then convert it back to t, and then you solve your differential equation. There's a lot of different ways that you can do that, and the first basic way of what a Laplace transform actually is, you're not really going to have to worry about it because we're going to use the table, but just so that way you know the definition, the way that they get all of these things is from this formula right here. So you take the integral from 0 to infinity of e to the negative st of f of t. That's going to equal the Laplace transform, or your L of y. L of y. So when you do this integral, you get some function, and then it's going to turn everything into your s's. So that's how you're going to get from this step to this step. And you're not really going to have to worry about it unless the question specifically asks. Use the definition of Laplace transform to find this. We can do one simple example, just so you know how to do it. And 0, and this 0 is going to be from 0 to 2. This is going to be from 2 to 5. And then this is going to be t is greater than 5. Okay. So we're going to be plugging this piecewise function into this formula up here. So we're going to break up the integral because we have an interval from 0 to 2, an interval from 2 to 5, and then from 5 to infinity. And if you add all those together, it's going to equal the integral from 0 to infinity. So we're going to break that up into, the first part is going to be the integral from 0 to 2 of, our function is just these values here. So it's going to be integral from 0 to 2 of e to the negative st times our f of t, which for this interval is 0, times dt. Then the next part is going to be from 2 to 5, e to the negative st times 3, because that's our function for that interval, dt. And then the third one's going to be the integral from 5 to infinity of e to the negative st, again, times 0 dt. Okay? So now, first and the third one are nice and easy because you're taking the integral of 0, so those are just all going to go to 0. That goes to 0, that goes to 0. So we don't really have to worry about any of those for this transform. So this is going to be the term that we're really looking at. So I know that I can take my 3 out in front because that's a constant. So I'm just going to rewrite this integral up here. So we have from 2 to 5 e to the negative st times 3 dt. So I'm going to pull my 3 out in front. It's a constant. And then I have to take the integral of e to the negative st dt. And all that I'm going to do for that is I'm treating this s as a constant, because we're taking the derivative, the integral in terms of t. So think of this as if it was just like e to the negative 3t or whatever. We're taking the integral, so I know that this is going to be e to the negative st over, technically over negative s, but I'm pulling this negative up top. So it's going to be negative e to the negative st over s. And then we still have this constant of 3 out in front, so I'm going to bring that down. And then this is going to be, our bounds of the integral are from 2 to 5. So now we plug in 5, then we plug in 2, so we're going to get 3 times negative e to the negative s times 5 over s minus negative e to the negative s times 2 over s. And all we're going to do is we're just going to simplify this down to become 3 e to the negative 5s minus 3e to the negative 2s all over, I'm going to throw this negative out in front, and an s on bottom. So this is your Laplace transform of this piecewise function right here. So I'm going to move over to the side so people think plus.
Minus, plus.
Well, no. So you have minus, minus here. I factored out this minus to the front. So this minus and this minus, I factored it out to the front. So that way you still have a minus in the middle. Does that make sense? Because that came out here. This should be, sorry, that should be like that.
Minus here, minus 3e. That's an S.
Yeah, that makes sense.
Go back to the
Purple? Is that better?
Yes,
So in case anybody can't see, like the final answer, it's everything is in parentheses. It's negative 3 times e to the negative 5s minus 3e to the negative 2s over s, and that whole thing has the negative out in front of it. Has everyone got that? Are there any questions? I know we have a lot of people in here, but if you have questions, raise your hand, let me know, and I'll try to explain it. Cool. So, where this Laplace transform table comes from is if you were to put each one of these functions into this equation right here, you would get out what's on the right side. So, for the rest of the night, we're not going to have to worry about this formula here because we're just going to refer to that table. So the next thing that I'm going to go into is when they give you a differential equation and they ask you to solve it using Laplace transforms. So with those types of problems, you have to use Laplace transform and then you maneuver it around and then do inverse. So first step, we're going to do the transform, then we're going to learn about inverse, and then we're going to do the second step and do the inverse. Okay? So can I erase this? Does everybody have this copy down?
Yeah.
Okay. So this next step is going to be, for an example, when they give you an equation such as y double prime plus y prime minus 2y is equal to 4. And then they'll give you some initial conditions. Y of 0 is equal to 2, and y prime of 0 is equal to 1. And it tells you to solve this using Laplace transforms. So you might be able to solve this using undetermined coefficients. It's something we've done in the past, but for this test, they want Laplace. So the first thing that you need to know is how to convert each of these into Laplace. So what we know, we're going to say that our y double prime in terms of Laplace, we're going to take the Laplace of that. It's going to be equal to s squared times capital Y of s minus s times your y initial minus your y prime initial. Okay? And I'll explain this out. I'm going to write out what the other two are. So like if it's just y prime and then if it's just y, and then I'll explain where all that stuff comes from. So if you're taking the Laplace of just your y prime, it's just going to be s y capital Y of s minus y initial. And then if you're taking the Laplace of just y, it's only going to be capital Y of s. Okay? So the way that you can remember these and which one goes to which, so when you're taking the Laplace transform, the power of the power of the derivative, so here we have y double prime, is going to be what your s starts off as. So here, since we have double prime, your s starts off squared. And then with each term, it's going to go down by 1 until you have 0 s's left, and that's going to be your last term. That's when you know when to stop. And then your first term also starts off with your capital Y of s, which is just your Laplace transform of s. This is what or your Laplace transform of your function. This is what we want to get by itself, so that way we can do the inverse Laplace to get our final y of t. But we'll do that later. So you have your s squared times your capital Y of s. Then you have to subtract everything else after that. You subtract away your, since we start off s squared, then we go down to s, and then we multiply that by our first initial condition. So our initial condition that's not the derivative. We just want y of 0. Then the next term is our y prime of 0. And if we were to say have a third, like y to the third, y triple prime, then the next term would be minus y double prime of 0. But you're never going to have anything that's high the power. Okay? So that's where this one comes from. And then you look at your Laplace of just y prime. So it follows the same rule. Since we have y to 1 prime, we start off with s to the first power, and we start off with a capital Y of s. Then we go down 1 power with our s, so that goes to 0 here, and it's just y of 0, because that's the next term that we have up there. And with our just Laplace of regular y, since we have no primes, there's no s's to start, so we just have our y of s. Does that make sense? Even if it doesn't make sense and you memorize it, you know what? That works too. So we know that the Laplace of our y double prime is equal to that. So I'm going to take this whole thing and plug it in for there. Then I'm going to take this whole thing for our y prime and plug it in there. And then I'm going to take my y of s and plug it in for that y. Okay? So now I'm going to rewrite that whole thing over here. We're going to have s squared capital Y of s. I'm going to put this all in parentheses. Minus s y of 0 minus y prime of 0. That's all my y double prime term. Then I'm going to add my s y of s minus y of 0. That's all my single prime term, and then I'm going to do minus 2 times capital Y of S. And that's all going to be equal to, since we're taking the Laplace of the left-hand side, we got to do the same thing to the right-hand side. So that's going to be equal to the Laplace, the Laplace of 4. So now a lot of times on the right-hand side, you might have something that you're, like a function of t that you're actually going to have to take the Laplace of and do the transform. And that's when it gets a little bit trickier. But since this is just the first example, we're starting off with the constant. So it makes the transform to the right side a little bit easier. So now the whole idea of converting to Laplace to solve the differential equation is we want to get this y of s by itself. Because if we have y of s is equal to something, then we can do the inverse Laplace of this to end up with just our y of t, which is going to be our function. That's the answer to this differential equation. So since we want to get the y of s by itself on the left-hand side, now is when we have to do all of our algebra and get fancy with some stuff. Because we need to get these y of s's by themselves. Okay? So the first thing that you do is you can plug in your initial conditions for your y of 0 and your y prime of 0. That's given up here. And then you can move those over to the other side, because those are all just going to be constants or constants times s. So I'm just going to rewrite this with my initial conditions plugged in. So we have s squared, capital Y of s, minus y0 is 2, so 2s, minus y prime of 0 is 1. This is going to be plus s capital Y of s, minus my y0 is 2. And this is going to be minus 2 capital Y of s. That's going to be equal to, again, the Laplace transform of 4. I think it's just going to swing. Okay. So now I'm going to take all my constants and all my terms that don't have a capital Y of s. I'm going to move them over to the right side. So I'm just going to be left with s squared capital Y of s plus s capital Y of s minus 2 capital Y of s. And then the right side is going to be equal to the Laplace transform of 4. And now I'm moving this over, so I'm going to have plus 2s. I'm going to have plus 1. And I'm going to have plus 2. So I'm just going to combine these to be a plus 3 to make life easy. Okay? So now we're getting closer to having just a y of s by itself on the left-hand side. But we still have some other terms there, so what I'm going to do is I'm going to factor a capital Y of s out of each of these terms. So I'm going to be left with capital Y of s times s squared plus s minus 2, just leave that hanging, is equal to the same left-hand side, or same right-hand side, sorry. And now the last thing you have to do to get y of s by itself is divide this over to the right-hand side. And one little trick that you can use to check yourself to make sure that you did everything correctly with all these steps, this term that you divide over to the right-hand side after you factor out your capital Y of s should look very similar to the function that you started with. So if you notice, we start off with the y double prime here, we have an s squared here. We start off with the y prime here with no coefficient, we have just an s to the first power with no coefficient. We have minus 2y here, we have just a minus 2 here. So it's almost, you can think of it as your auxiliary equation when you're doing like your m squared plus m whatever. That's what it's supposed to look like, but with your s's right here. So that's just a way to check yourself to make sure that you got, as of right now, you're at the right step. Okay? So then you divide that over to the right side and you're left with capital Y of s is equal to Laplace of 4 plus 2s plus 3 all over s squared plus s minus 2. Okay. Does it make sense up to here? We're all good? Okay. So now what I'm going to do, just to make everything on the right-hand side look the same, I'm just going to take the Laplace transform of 4, just so that way I have everything on the right side in terms of just s's and constants. So the way that I do that is I come over to my Laplace transform table. So I look and I see that 4, which one of these does it match up? 4 is going to be my S of t, so I have to see which one of these looks closest to 4. And I'm going to say it's 1. And I'm going to say that this Laplace of 4 is just the same thing as 4 times the Laplace, 4 times the Laplace of 1. Because you're allowed to pull constants out of the Laplace. So I know that the Laplace of 1 from right here is just 1 over s. Multiply that by 4, you just have 4 over s. So I'm just going to erase this right here and replace it with a 4 over s. So we have just 4 over s. Okay? But I still don't like the way that looks because I don't like complex fractions. So what I'm going to do in order to get rid of this s in the denominator right there is I'm going to multiply both the top and the bottom by s. Because technically, since we're multiplying by something over itself, you're multiplying the whole fraction by 1. So you're not actually changing the value. But by multiplying by s over s, you can get rid of this 4 over s complex fraction. So you're going to be left with y of s is equal to 4 plus 2s squared plus 3s all over s cubed plus s squared minus 2s. Okay. So now we get to this step. We have our capital Y of s on the left-hand side. We have everything on the right side in terms of constants and s. So this is the point where we're going to be going into our inverse Laplace. Because now we have, if we take the inverse Laplace of our capital Y of s, we're just going to be left with y of t, which is going to be the answer to our problem, the answer to our differential equation. And then we have to also take the Laplace on the right-hand side. We're going to get something in terms of t, and that's going to be our answer. Okay? So in order to do the inverse Laplace, I'm going to erase this part. So I'm just going to rewrite that up here. Capital Y of s is equal to, and I'm just going to reorder it. So we have 2s squared plus 3s plus 4 over n, I'll just rewrite that. S cubed plus s squared minus 2s. Okay? So this problem actually touches upon the next thing that's involved in Laplace, which is partial fractions. So I'm just going to keep going through with this problem, and if you have any questions about specific partial fractions, anything like that, I'll go over it more specific things with partial fractions later. But if you have any questions about this specific problem, let me know. I'm going to try and walk it through and explain it as I'm going through. So in order to do partial fractions, we want the bottom to be as factored as it can be, and we want the top to be as simplified as it can be. So right now, this top, we can't combine any more like terms. We can't get rid of any denominator. The numerator is as factored as simplified as it can be. So the numerator is good right now, okay? Because we worked on simplifying it all over here. So right now we have a nice simple numerator. But this denominator we need to factor. We need to get it into as factored terms as we can. So the first thing that I'm going to do to factor this is I'm going to pull out an s. So I'm going to have s times s squared plus s minus 2. Okay? Now I look at that and I say, okay, I think I can still factor this a little bit more. So I know that I can do that with product sum. So I'm going to have s times, it's going to be, yeah, s plus 2, sorry, s minus 1, I had a little brain fart there. Yeah. So that's, because multiply this out and get s squared. Here you'll have s minus 1, or positive 1, minus 1s, sorry, positive 2s, which would add to that, and that would be your minus 2. So this now becomes your denominator, because it's as simplified as it can be. So just to save space, I'm going to erase this and replace it with that. So I'm going to get rid of that. I'm going to have s times s plus 2 times s minus 1 is going to be a new denominator. So now we have the top is as simple as it can be, the bottom is as factored as it can be. So the top and the bottom are both good. We're ready to go into partial fractions. So in order to do partial fractions, what we're going to say is we're going to take, we're going to set the denominator for each of 3 terms to be one of these factors. And we're going to say we don't know what the numerator is. That's what we're going to try and find out. So we're going to say set this equal to a over s plus b over s plus 2 plus c over s minus 1. Okay? And we need to figure out a way, or we need to figure out what all 3 of these are. Because these 3 terms are now much simpler than this one. So eventually when we find out what these 3 numerators are, we can take the Laplace of each one, add them all together, and we're going to end up with our y of t. So all of these steps are involved in order to find the answer to this problem. So first step in partial fraction decomposition, after you separate everything, is we want to get rid of the denominators. So what you have to do to get rid of the denominators is multiply every term by the full denominator. So when I multiply this left side by the denominator, it's going to cancel out with the whole bottom. So all that I'm going to be left with is 2s squared plus 3s plus 4. If I multiply this by the whole denominator, so I multiply it by s times s plus 2 times s minus 1. So times s plus 2 times s minus 1. Since I have an s in the numerator and s in the denominator, those are going to cancel out, and I'm going to be left with a times s plus 2 times s minus 1. Okay? So I do the same thing with the b, and I do the same thing with the c. And again, in both cases, the factor that it has underneath it is going to be the one that cancels out. So we're going to have plus b times s minus 1. And then plus c times s plus 2. That's an s plus 2 if you can't read it. Okay? Have I lost anybody yet? Good. So there's a couple different ways that you can solve it from here. You can either multiply this out and you get a bunch of terms with s squared, you get a bunch of terms with s, a bunch of terms that are constants. And then you can solve it just like you do with undetermined coefficients. Take all the coefficients in front of an s squared, set them equal to 2, because you have 2s squared on the left side. Take all the terms that are just with s, take all the terms that are just constants, the same exact way that you would do with undetermined coefficients. In a problem like this, an easier way to do it is just pick values for s that are going to make things cancel out. So what I mean by that is if I'm assuming a value of s to be equal to 1, okay? I'm plugging s equals 1 into this entire formula. And the reason why I'm choosing 1 is because if I plug in 1 right here, 1 minus 1 is going to be 0, and this whole term with a in it is going to cancel out. And then I no longer have to worry about my unknown of a. And then right here, this s minus 1 is also going to be 0, so this whole term with b is also going to cancel out. So then when I plug this 1 in over here, and I plug it into the whole left side, I'm going to have 2 times 1 squared plus 3 times 1 plus 4 is equal to, that's all 0, and it's just going to be c times 1 plus 2. And now, simple algebra, this is just 2 plus 3 plus 4 is equal to 3c. 7, 9 is equal to 3c, and you get c is equal to 3. Then I found what my c term is, so now I want to pick something else that's going to make 2 different terms cancel out. So I see that this is being multiplied just by an s, and that's just by an s. So if I set my s equal to 0, I know my b and my c are both going to cancel out because they're going to be multiplied by 0. So I can plug in 0 for the left side, and if I do that, this term's going to go to 0, this term's going to go to 0, and all I'm going to be left with is 4 on the left-hand side. And that's going to be equal to, on the right-hand side, now we have our a, but our b's gone and our c's gone. So we're just going to have a times 0 plus 2. So that's just a times 2 times 0 plus 0 minus 1 is just negative 1. So that means 4 is equal to negative 2a, which means a is equal to negative 2. And now we only have one term left to find, which would be our b. And in order to find our b, we need to pick something that's going to cancel out our a and c. So I know that that's going to be negative 2 if my s is equal to negative 2, because that's going to make this term be 0, which means all of my a's will be 0. And again, it's going to make this s plus 2 be 0, which all my c's will be 0. So if I choose, I'm going to squeeze it in right here, s is equal to negative 2. I then again plug it in on the left side. I'm going to have 2 times negative 2 squared plus 3 times negative 2 plus 4. And that's going to be equal to my b times negative 2 times negative 2 minus 1. Okay? So I know that negative 2 squared is 4 times 2 is 8. Minus 6 plus 4 is going to be equal to, that's negative 3 times negative 2 is 6. B. So this is 6 on the left side is equal to 6b. So I get that b is equal to 1. Sorry if that went a little low. So what I just did with all 3 of these steps is I figured out what these 3 coefficients are. Now, a lot of times when it's a more complicated example, you're going to get something up here with an s in it. You may or may not. Or these are going to be something more complicated. But this is a nice, simple example where it's just one constant on top of each one. Nothing else that you're going to have to worry about. So we're almost done. We got one more step left. Is we got to plug in all 3 of these, our a, b, and our c, to right here, then take the Laplace of each one. So I'm going to come over here and erase a little bit. I'm going to erase this side, if everyone's good with that. So now I'm just going to rewrite this ABC with our A, B, and C plugged in. So I know that my capital Y of S from right there is going to be equal to negative 2 over S plus 1 over S plus 2 plus 3 over S minus 1. And now we want to take the Laplace of the left-hand side, so that way we can get our y of t. It's going to equal the Laplace of everything on the right. I'm not going to rewrite all that. But in order to find the Laplace of everything on the right-hand side, we can do each term individually. So the first thing we got to do is find the Laplace of negative 2 over s. Or sorry, the inverse Laplace. Because we already have an s, we want to get it back into t's. So since we already have an s, we want to get back into t's. We look on the right side, and what looks most similar to that, and we say this 1 over s looks most similar to that because I know that I can just pull the negative 2 out in front. So I'm going to say that this is the same thing as negative 2 times the inverse Laplace of 1 over s. Okay? And I know that the inverse Laplace of 1 over s is just 1. So this whole thing just becomes 1, and I'm just left with negative 2. So that is my Laplace of the negative 2 over s. So I'm going to pull that down, and I'm going to say my y of t is equal to negative 2. Now we've got to find what it is for this term, and then that term, and that's going to be our answer. I'm in a board space. So now I'm going to take the Laplace of my inverse Laplace of my 1 over s plus 2. So now I look back over here and I say, what does that look most like? And I say, okay, I have a 1 over s plus something. And I say, okay, this looks really close, but this is an s minus something. So what I'm just going to do is I'm going to rewrite this as 1 over s minus negative 2. Because s minus negative 2 is the same thing as s plus 2. So I have that, where this is my a value. So I know that this can just turn into e to the negative 2t. And that's the transform for that one. So I'm going to bring that up, put it right here. So I have my negative 2 plus e to the negative 2t. Now I got one term left. We got to find the inverse Laplace of 3 over s minus 1. So again, I'm going to pull this 3 out in front, so that way I have 1 on top, and that way it can look like that transform. So I'm going to say that this is the same thing as 3 times the inverse Laplace of 1 over s minus 1. And I know that this transform is just going to be equal to e to the positive 1t. So it's just e to the t, and you bring down the 3 in front of it. So that's the transform of the last term. You add it on right here, 3 to the et. And that is your final answer for this differential equation. All that crap we just did was to solve for that. So I know that problem covered pretty much everything that you're going to have to do with Laplace except for unit step functions. I'm going to go over a little bit more in detail some of the specific things, like I'll go over more things that you need to know for partial fractions. We'll go over another example where the transform part, the inverse transform, is more difficult. But if this question made sense to you and you understood what was going, what each step was about, what the purpose was, that's going to be very good. Okay? Are there any questions about that whole problem? Any part in there? Anybody confused at all? Cool. Okay, so the next thing that I'm going to go over is some more complicated inverse Laplace transforms. Over here it was nice and easy because the only thing that we had to do in order to convert something to something, to convert each of the terms into something in the table, was just factor out a constant. But there are going to be times where you have to do more tricky things, where you're going to have to force it to look like something. And a lot of kids can get confused during this stuff because you're doing things that you don't normally do. You have to change it from looking like one thing to looking like another. So one example that is very good for this one is this one right here. We got to take the inverse Laplace of 3s plus 5 over s squared plus 4s plus 13. So, remember what I said before, when we're going to take the inverse Laplace, the first thing that we want to do, and when you're doing partial fractions, but that's not going to come into play in this one, we need to get this to look like something on this table. And right now, that doesn't. So, one thing that you might think to do is partial fractions to simplify it. And you would run into a problem because you would find out that this is going to be a little bit more difficult to factor than some of the other ones. It's not just a straight product sum. But for this one, you're not going to need to do partial fractions. This is going to be one, like I said, where you're going to have to force it to look like something. So one thing that you might find yourself doing is, for this, you need to use completing the square. So we're going to factor that by using completing the square. But the key idea is we can't change the value of it. So whatever we get at the end, it needs to be equal to s squared plus 4s plus 13. So we can multiply things, we can add things, but at the end, if we were to combine all the terms, we need to get that same value. We can't change the value of it. So in order to complete the square, if you guys remember, you take your b, which is the coefficient in front of just your single variable. So you take this, you divide it by 2. So I take that divided by 2, that's going to be 2. And I know that s plus 2 squared is going to be something involved in this problem. So this is the first step. You take the b divided by 2, then you have s plus 2 squared. Now, in normal completing the square, you would then add something to the left side, add something to the right side. But we're not concerned with that as much because we're not dealing with an equation. We're just trying to rewrite this. But the key thing is we can't change the value. So this s plus 2 squared, if I were to multiply this all out, it would be s squared plus 4s plus 4. Well, we just said that we can't have it equal that because we need to have this equal that. So what can I do to this bottom in order to make it equal to the top? Add 9, right? So I want to keep this by its, I don't want to change this at all. I'm just going to write a plus 9 at the end. So I know that this whole term here is equal to s plus 2 squared plus 9. So now if I were to rewrite this, we need to find the Laplace of 3s plus 5 over s plus 2 squared plus 9. So now, ideally, the purpose of this was to get this to look something more like something on this right side of this table. So I'm looking at these and I say, okay, that definitely does not look like that. No, it doesn't really look like that because we have something squared plus another constant. This is close, but the s isn't squared, so I don't like that. Okay, that looks like it could be something because I have an s squared saying plus b squared. Well, I know that 9 is just 3 squared. So you know what? Let me rewrite this as just 3 squared. So that way I can say it's something similar to what we have here. And then I say, okay, well I have cosine is also something close to that, where I have an s over s squared plus a constant squared. So, okay, so I'm seeing something I like about this sine and cosine. So what we're going to do is, I know my teacher in high school called it sharing the love. We're going to split this fraction up. We're going to make this one fraction, and we're going to make this another fraction. It's called sharing the love. Kind of looks like a heart. That's the way I learned it. I know it. So I'm going to rewrite this as, separate this off. We're going to have 3s over s plus 2 squared plus 3 squared plus 5 over s plus 2 squared plus 3 squared. Okay? Okay. So now we're looking at this, and we say, okay, well here I can pull this 3 out in front, and I'm going to do that right now, just because we know that with Laplace, can pull constants out in front, doesn't change anything. So now I'm looking here, and I say, okay, well I have an s on top, s squared plus b, so this term is going to be something with my cosine. Okay? This is going to be something with cosine. And on the right side, I see a constant on top, and an s plus 2, and b, and some constant squared. So this is going to be something to do with my sine. But we're not quite there yet, because I see that in my cosine term, here I just have s squared and s squared. But here I have s plus 2 squared, and on top is just s. So we need to make anywhere that I see an s needs to be in terms of this s plus 2. So what I'm going to do is, look, now it's an s plus 2. We're all happy, right? Unfortunately, we can't. It's not that simple because we just changed the value of it. We just added 2. Well, the way that I'm going to account for that, I'm just going to subtract 2. There we go. Now that works. Because now we have this s is in terms of s plus 2, but we didn't change the value because we have minus 2. So we didn't change the value of the numerator. This numerator still equals s, which is what we started with. But I can't really take the Laplace transform of this yet because this doesn't say that I can have an s term and a constant in the numerator. So what I'm going to do is I'm going to take this minus 2, I'm going to bring it over there. Because this is just a constant on top with the same denominator. So I'm just going to say, okay, I'm just going to move that right there. And remember that it's still 3 times that. So this should technically be 3 times 2. I'm going to write that as a 6. Because we have 3 times s, 3 times 2, 3 times our minus 2. So when we bring it over here, it becomes a minus 6. Does that make sense? Yeah. So we had this right here, right? We're at this step here. And when I bring it over here, this is technically right now 3 times this minus 2. So when I bring it over to this term, it's still going to be 3 times minus 2, or in other words, a minus 6. Does that make sense? I confuse anybody with that. Okay. So now I'm just going to rewrite this as just minus 1. Just make life easier. Okay. So now this is starting to look like something that I can take a Laplace transform on. So I look here and I say, okay, well my s is all in terms of the same thing. And I have s over s squared plus b squared. Where my b is 3, my s is now s plus 2, and everything else looks the same. So now, this term right here, I'm ready to take the inverse Laplace of. So I say, okay, I'm going to keep this 3 constant, bring it down in front. And then I'm going to pretend, anytime you have your s's in terms of s plus 2, s minus 1, s plus or minus any constant, ignore that constant at first. We're going to account for it at the end by doing that. And I'll explain that. So first thing, we're going to ignore this. We're going to think of this as just as if it was s over s squared plus b squared, where our b is 3. So I know that means it's going to be cosine of bt. So this is going to be cosine of 3t. Okay? But now, in order to account for the fact that we have this plus 2, we have to look to this transform here. And what this transform says is if you have Laplace, if you're taking the Laplace transform of something that's in terms of s minus a, all you have to do is do the normal Laplace transform and multiply it by e to the at. It's as simple as that. So I look at this, and I say, okay, I took my normal Laplace transform, and I just have to multiply it by e to the at, where my a is negative 2. So e to the negative 2t. Does that make sense? And that's just coming from this transform. So now I have this whole cosine term done. So the first part of my answer is going to be 3 cosine of 3t e to the negative 2t. Okay, now we're going to work on this right side. So we're going to do the same thing. This looks like my sign because I have b is a constant, and I have a constant over some s squared plus some constant squared. The only thing is, this b needs to be the same thing as that b. And right now, my b here is 3, and that's not a 3. So what do? There we go, now it's a 3. But you can't do that, because again, we changed the value. So what I'm going to do, in order to not change the value, I'm going to multiply it by 1/3. Because 3 times 1/3 is just 1, and that's what we started off with. Does that mean this is where all the force math comes into play, and a lot of kids get confused on this. So if you have any questions, please write yes.
Does the sign not matter?
The negative? So the negative, doesn't matter really right now because we can just pull this out and make it minus right here. So you can, the sign's not really going to matter because you can just pull the negative out in front. Any other questions?
Oh.
Yes.
Can you explain the 3 and the 1/3 part again?
Yes. So right here we started off with, it was originally -1, but I pulled the negative out in front, so now we just have a 1 on top, right? But I know that in order to do, I want to do the sine inverse transform. In order to do the sine transform, I need to have b over s squared plus b squared. Well, on the bottom, I see my s term squared plus a b term squared. But this is telling me that my b is going to be equal to 3. So if my b is going to be equal to 3, that means in the numerator, I need to have my b. So in the numerator, I need to have a 3 in order to be able to do the transform. So I need to have a 3 up here in order to do the transform. But I can't change the value of it at all because then we're changing the answer. So the way that I'm going to do this is I'm going to say that 1 is the same thing as 3 times 1/3. Right? So all I'm doing is I'm rewriting this 1 as 3 times 1/3. I didn't change the value of it at all. It still equals 1. But now I have a 3 that I can use. And we know that when we're doing Laplace transforms, we can pull constants out in front whenever we want, if it works out for us. So I want this 3 to stay here, but I don't want this 1/3. So what I'm going to do is I'm going to pull this 1/3 out in front. And I'm just going to have minus 1/3 times this whole thing. Does that make sense? Because all we did was we pulled this 1/3 out in front. So it's still being multiplied by the 3, so we still have our 1 value on top. But now we have something inside the parentheses that we can take the transform of. We can do Laplace. Okay? So I'm looking at this just to make sure everything's good. I got my s squared plus b squared on bottom. When my b is 3, I got that same b on top. Where it's 3, I can do the transform. And again, this s plus 2, we ignore it to the end because it's just going to be multiplying by that e to the at. So we know that this is going to be equal to 1/3, because we have that 1/3 out in front right now, actually negative 1/3, times sine of 3t. And then in order to account for the s plus 2, just like we did over here, we're just going to multiply it by e to the negative 2t. So we just bring that term right here, and it's going to be minus 1/3 sine of 3t times e to the negative 2t. And that is your inverse Laplace transform for this function right here. Does that make sense? Yeah, I got it. Does that make sense? So this is going to be something just for this type of question where you had to force something like this. Last year on my test was worth 10 points out of 100.
So you're telling us to skip it?
Well, no. Then the best you can do is a 90. So you want to try your best. But, yeah,
Was the question literally just solving an inverse Laplace transform?
so yeah, last year, like before you guys leave, make sure you sign in on the laptop. It's going to be by the door when you're leaving. But I'm going to send you out the notes from this review, and I'll also scan my entire test and send it out to you. And you'll see, we had, like question 1 was broken up into parts A and B. Question 2 is broken up into parts A, B, and C. And all of like the individual parts were just like an inverse Laplace transform where this one involved partial fraction decomposition. And then part B might have involved having to do unit step function. And part C might have involved having to do forcing things. So there was a lot of like small inverse Laplace transforms that all had to do with one weird thing that is involved with Laplace. So you can see, you'll see that when I send out my test. But like part A, it was just you have to know partial fraction decomposition. B involved with your whole like solving, like with your s squared y of s minus sy prime. Question 2 had to do with step function. Question 3 or 2D had to do with step function. So it was a lot of small Laplace stuff, not a lot of big questions on Laplace. There was one big question about separation of variables, and there was one big question about eigenvalues, and that was the test. But you guys will see that. I'll send it out to you if you guys don't already have it from your friends from last year. Okay? Anything else? So the next thing that I'm going to go into is partial fraction decomposition. We touched upon it a little bit in the last problem, maybe one of the other problems, but I'm going to go into just some of like the little things that you have to remember, because like the little tricky cases that they can give you on the test. So if everybody's good, I'm going to erase everything that we have up here. I don't think I see anybody writing down anymore. Okay, so getting into partial fraction. Partial fraction decomposition. Yeah. Let's go right to unit step function. This is going to be like 2 minutes. I'm not going to do an example for it. I'm just going to show you like 1 or 2 key things that you need to know. Okay. So when you're doing partial fraction decomposition, I'm not going to do a full example for this. I'm just going to show you one key thing that's probably going to show up on the test. So if you're given, I'm making this up so the numbers probably won't work out. You're given something 3s plus 5 over s plus 2 squared times s squared plus 3s plus 5. Okay? Say you're given this, and you know that you have to do partial fraction decomposition for this. When you are choosing, so this is as factored as it can be right now. We can't simplify the denominator anymore. So we're going to set a over 1 factor. But you're looking at this s plus 2 squared. The way that you account for the fact that it's squared is you do a over s plus 2 to the first plus b over s plus 2 squared. So anytime you have a whole factor that's squared, that's what you have to do. Even if it's just an s, you'll do s and then b over s squared. Okay? So that's one thing that they can throw at you involving partial fraction. The other thing that they can throw at you is something like this. If you have a factor that's to the second or to the third power, where the highest order is bigger than 1, I'm just going to write it down here. This is going to be plus cs plus d over s squared plus 3s plus 5. So the key thing to remember is the highest power on top has to be 1 lower than the highest power on bottom. So normally, the highest power is just s, so here we don't need any s's, it's s to the 0. But here, since we have s squared, we need an s on top, and then we need every term after that. So if for some reason you were to have an s cubed on bottom, you would need cs squared plus ds plus e. Does that make sense? So those are just two different things that they can throw at you with partial fractions that aren't normal. Two tricky things they might throw at you. Okay? So without further ado, we're going to go on to unit step functions. Okay, so this is very similar to one of the problems that I had on my test last year. And basically, it wanted you to find, so it gave you some function on the left and it wanted you to find y of t. Right now, we're just going to write out what the unit step function would be for this. So the whole idea of unit step functions is it's a way to turn on a function and turn off a function. So it's a way to represent a piecewise function in one line, as opposed to drawing it out like this. So the way that you got to do it is we're going to say that our y of t, our y of t is going to be equal to, you take the first function, so in this case it's going to be 3e to the t, and you multiply it by u of t minus, and this first thing that you put here is where the function turns on. So in this case, it turns on at 0 because it's active from 0 to 2. So we're going to write t minus 0. A lot of times you'll see that written as just u of t. I'm just going to put the t minus 0 so you can see where it's coming from. So then it's going to be this minus u of t minus where it turns off. And since this function turns off at 2, it's t minus 2. And then plus our second function, which is just 0, and no matter what that's multiplied by, it doesn't matter. But say if this was an actual function, then we would do the same thing. We would do u times t minus where it turns on, which is at 2. And since it doesn't turn off, we don't have to worry about where it turns off. So if we were just to try and find our y of t for this case, we would just have 3e to the t times u of t minus 3e to the t times u of t minus 2. So this is a very basic example of just writing out a piecewise function as a unit step function. Now, one of the key things is it doesn't come into play in this problem because we're not having to do Laplace. But if you were to take the Laplace of this bottom transform comes into play. In order to take the Laplace of something that's being multiplied by a unit step function, the t's in your function have to be in the same terms as the t's in your step function. Now this is very important, and it's going to come back into play with forcing things to look like other things that everyone hates. But so this part right here is fine, because in my unit step function I have u of t, so all of my t's are just our t's, which is good. But in this part right here, my unit step function, I have t minus 2. So this t right here needs to look like a t minus 2. So the way that can happen is this negative 3 e to the t u of t minus 2. We need this t to be in terms of t minus 2 in order to be able to take the Laplace of this function right here. We're not actually going to take the Laplace, but we need to get it in the right form. But again, when I added that minus 2 to the exponent for the e, I changed its value. So I need to multiply this or add something or do something to this so that way I get it back to the original value that it was up here. And I can't multiply it by anything with a function of t, because then that t would have to be in terms of t minus 2, and it creates a big shit show. So what I know is e to the t minus 2 is the same thing as e to the t times e to the minus 2. And that's just basic exponent rules. If you have two things that are added together, you can multiply them together, and that's easy. So, since I don't want to change the value of this whole thing, I want to also divide this by e to the minus 2. So now e to the minus 2 is a constant, and I know when it's Laplace, I can pull constants out in front, so it's not going to change anything as long as it's a constant and not a function of t. So technically, if I were to simplify this e to the minus 2 and e to the minus 2 would divide out. So we'd be left with still the same value that we started with, and it would work out well. And in order to take the Laplace of this, I would just pull this negative 3. I know that 1 over e to the minus 2t is just e to the positive 2. So I just write that, and then this would all be times e to the t minus 2 u of t minus 2. So then I would take the Laplace transform just e to the t, and I would have that as my coefficient out in front. Does that make sense? Yeah.
Where's the, I'm still a little confused about how you put the negative 2 in. Like, where did you,
Yeah. Well, so this part is already good.
okay, all right. So
Yeah. So this is from there. This we don't have to fix because we already have u of t. This is already t. So that's fine. This we have to fix, and that's where we came down to.
These t's
Does that make sense?
doesn't matter about us.
So if we were to do the Laplace of the whole thing, we would take the Laplace of this left half, then we would take the Laplace of this right half, which we converted to be this form. And then you would add those two together, and that would be the total Laplace. So now, going the other way with unit step functions, if you need to do the inverse Laplace, this is what it's going to look like. So this was another problem that we had on our test last year, and it said this was literally all that was written on the page. We have to take the inverse Laplace of s plus pi over s squared plus pi squared, all times e to the negative s. So we need to take the inverse Laplace of that. So one thing that should spark in your mind is anytime you see an entire Laplace function being multiplied by e to some power of s, some coefficient times s, this is going to indicate that you're going to have a unit step function. Because when we're doing unit step function, we can take the Laplace of our normal function and then multiply it by e to the negative s. So since we're being multiplied by e to the negative s here, negative as here, to come back over here, this is indicating that we're going to have a unit step function. So what I'm going to do is I'm going to rewrite this as just s plus pi over s squared plus pi, all times, or pi squared, sorry, e to the negative s. And according to this transform down here, I can just take the inverse Laplace of everything else, put it in terms of t minus a, where a is the coefficient here. So this is just -1. So that's your 1 is your a. Take the Laplace of that, put it in terms of t minus a, and then multiply by the step function of t minus a. So what that means is I'm going to forget about this for right now, and I'm just going to take the inverse Laplace of this. So in order to take the inverse Laplace of this, I say, okay, again, I'm going to share the love, because I'm looking at this, I see s squared plus a constant squared on the bottom. I know that this is going to separate into my sine and cosine, where my s is going to be involved in the sine, and the pi is going to be involved in the cosine. So I'm separating this into s over s squared plus pi squared, plus pi over s squared plus pi squared. And again, I'm going to save that for later. So this is in the exact form of my cosine transform, so I don't have to worry about forcing anything, I don't have to do anything else. I can just say that this is equal to the cosine of pi t. This is just equal to sine of pi t. So now what we did is we went from here to our f of t. But this transform tells us that this needs to be in the form of t minus a. So these t's, since we're now taking this into account, since this transform is being multiplied by e to the negative s, we have to account for that with these t's. So these t's are actually cosine of pi t minus 1, because our a is equal to 1, plus sine of pi t minus 1. So now this is different from what we did before. We're not changing the value of anything here. We don't have to account for this minus 1, because this term right here, the e to the negative s, is telling me that these t's are this. We're not changing the value or anything, but this is what it should look like. After we take the transform, we have to plug in that t minus 1. Okay? Now all of this is being multiplied by the unit step function of u of t minus a, which is just u of t minus 1. So when you're doing inverse Laplace transforms, and you're going to be using unit step function, you recognize that you're using unit step function because it's being multiplied by e to the negative some power or some coefficient times s. So you can pull that aside and ignore it for now, when you first recognize that that's what it is. Take the Laplace transform of everything else that you have, and then at the end, plug in for all of your t's, t minus a, where a is the coefficient, and then multiply it by u of t minus a. If you're doing the inverse Laplace transform with unit step function, those are the steps that you follow. Does that make sense?
Did you go to the last step one time where you added the
From here to here? So this Laplace transform is if I just had this right here.
Yeah.
But since this e to the negative s is present, it's telling me that these t's aren't actually t's, they're really t minus 1. So since I was ignoring the e to the negative s, I just had that, but now that I'm accounting for it again, I have to plug in my t minus 1 here. And then since I'm using step function, I also have to plug in the unit step function, obviously, at the end of u of t minus 1. Yeah. So if this was just e to the positive s, so now your a is technically now equal to negative 1. Because this is telling me that it's in the form of e to the negative as. So if I have a positive coefficient, then I have my a is going to be equal to negative 1. So if you have your a equal to negative 1, then you would just plug that negative 1 into here. So this would really just be t plus 1, t plus 1, t plus 1. That's the only difference. Yeah.
Do we ever solve for
Solve for that?
Yeah.
No, because all that this is saying is this is a way of representing something like this. It's a way of representing the piecewise functions. So this function is saying that it's turning on. So if I were to actually draw out what this is, so I'm not going to draw what the actual function is, I'll just use it as a constant. But this step function is saying that it's turning on at t equals 1, and then it's never turning off because there's no second term. So it would stay at 0 until you get to t equals 1, and then whatever the function is would start at t equals 1, and then it would be some sort of sine wave, sine curve, whatever.
So would that be your answer? Would you have to put in
This is, that was the final answer on the test. That was all that was to. So that one I kind of just wanted to introduce, I'm forcing it, but on our test they wanted us to actually take the Laplace. So you would take the Laplace of this, take the Laplace of that, and that was your answer. Does that make sense? Does anybody have any other questions on pretty much anything Laplace, anything unit step function? So I know this is taking a while, so I'm going to go with separation of variables. This is the answer that they want. For this, take the Laplace. Okay, so I had a couple people ask. So we're gonna take the Laplace of this, just do the last step that I didn't do before. So we got to the point where we had 3e to the t times u of t minus 3e squared minus 3e squared e to the t minus 2 u of t minus 2. Okay. So this is going to be the last thing I do with Laplace. This is just going from step function to the Laplace, taking the actual Laplace like that. So if I, guys, if we could settle down a little bit. Sorry. So if we're taking the Laplace of this, we ignore the fact that the unit step function's there. We take the Laplace of just that. Because that's what this is telling me right here. We can take the Laplace of my f of t minus a, and then just multiply it by e to the negative as. So I know that Laplace of 3e to the t, 3e to the t, right here, where my a is just going to be 1. This is just going to be 3 times 1 over s minus 1. Okay? And then since I now need to account for the unit step function, I multiply this by e to the negative a, which is 0, s. So since this term is multiplied by e to a 0 power, that's going to go away. So I don't have to account for a step function for this one because my a is 0. For this second term, it's going to be minus 3e to e squared because that's just the coefficient out in front. And now I take the Laplace of this e to the t minus 2, but I pretend that it's just a t because I can ignore the fact that there's a step function here for right now. So again, the Laplace of e to the t is just going to be 1 over s minus 1. Now to account for the unit step function, I just multiply it by e to the negative as, where a is 2, so it's e to the negative 2s. And this would be the Laplace transform. Yeah. It's only this right term because this first term is being multiplied by e to the negative 0s. So that's why I left it out, because it's technically 1. But this second term is where we're using the t minus 2. So only this second term right here is being multiplied by e to the negative 2s. So if everyone's good with Laplace, I'm going to go into separation. There's not much of separation. It's just like the beginning of the next stuff that you're going to do with all your wave functions and heat equations and stuff. But if everyone's good, I'm going to erase everything that's here. Good.
How long do you think eigenvalue takes? Very long. Eigenvalue is going to take the longest.
That's the way to go through all the cases. You have to go through all 3 cases.
There's 3 cases. You need to?
Yeah.
Yeah. Because an eigenvalue can work for case 1, 2, or 3. Like you have to go through a trial. Eigenvalue sometimes, like it will work for 1 and 2, but it won't work for 3. That means that so you have to do steps. There's 4 steps in eigenvalue. The 3 cases are only step 2. So you have case 1. Well, you have step 1, then the 3 cases are step 2. Then you have a step 3, and then you have a step That's what Ray did class when he did eigenvalues, and I think we lost it in 7 So Brady told us that on the exam it's a full course, not just side by cosine. That's the only thing I'm clear on that. So yeah, he said it's the full one, yeah. Well, did you guys look at the review sheet?
This is the problem that we had on our test last year.
It's online.
This is the problem that I had on my test last year for separation of variables. Separation of variables isn't too complex. It's going to be the same set every time. So we're just going to go through this one. If anybody has any questions, just let me know. So what this is saying is my function u is equal to x, which is a function of x, and times y, which is a function of y. And what it wants me to do, it says that the partial of u with respect to x plus the partial of u with respect to y is equal to u. So if I want to take the partial of this with respect to x, all that means is I'm treating my y function as a constant and I'm taking the derivative of my x. So all that becomes is x prime times y. Because I'm treating my y as a constant and I'm taking the derivative of my x function, and the derivative of my x function is just x prime. Now doing the same thing partial with respect to y is just going to be x y prime. And then that's just going to equal the same function, which is x y. Yeah.
Those, isn't that like little y's or big y's?
These are all big. If I make them little, I'm going to exaggerate it small. Yeah, these are all capitals. So the next thing that I want to do is I want to get it to the point where I have x prime over x on one side. I want to have y prime over y on the other side. Because that's the next step that you want to get it to be when you're doing separation of variables. So I want my y prime on the other side, so I'm just going to subtract that over to the other side first. So I'm going to have x prime y is equal to xy minus xy prime. And I say, okay, now I know that the next thing when I'm doing separation of variables is I want to have x prime over x, and I want to have y prime over y. So the way that I can get this x prime by itself over x is I can divide this whole thing by xy. Because now these two y's are going to cancel out, so I'm going to be left with x prime over x, which is what I want. So if I divide that by my xy, I have to divide every term by xy. And then I'm just going to be left with x prime over x is equal to 1 minus y prime over y. Okay, so once you're at this step, set it equal to negative lambda. There's some complex proof, and I'm sure they explained it in class, maybe they didn't explain it in class, why you can do that, because some ratio is always going to be constant. I really don't care. Once you get it to the step where you have x prime over x on one side and y prime over y on the other side, set it equal to negative lambda, where lambda is going to be a coefficient. So the next thing that you do from here is we're going to set up two unique equations where one's going to be x as a function of only x's, and the other one's going to be with y's, y primes, and only y's. So we're going to get two problems that we're used to solving where there's only one variable. So what I'm going to do is I'm going to take this, and I'm going to take this. So I'm going to say x prime over x is equal to negative lambda. So I don't like fractions, so I'm going to multiply this out, and I'm going to have x prime is equal to negative lambda x, and then I'm going to bring this over. So I'm going to have x prime is equal to, x prime plus lambda x is equal to 0. So this problem we know how to solve. Nice and simple. We can just say that m plus lambda is equal to 0. So I know that my m is equal to negative lambda. And therefore my function x is equal to some constant times e to the negative lambda times, this is a little x. That's a little x. And this is what your function x is equal to. So in your final answer, that's what your function x as a function of little x's is equal to. So then we're going to find what our function y of y is equal to. We're going to multiply those two together, and that's going to be what your u equals, and that's what the question's asking for. Okay? So we're going to do the same thing with our y's. Now we're going to take this part and that part and set them equal. So I'm going to say that 1 minus y, capital Y prime over capital Y is equal to negative lambda. So now I do the same thing. I don't like denominators, so I'm going to multiply everything by y. So I'm going to have y minus y prime is equal to negative lambda y. All these are still capital Y's. So I move everything to one side. I'm going to have y minus y prime minus or plus lambda y is equal to 0. And I'm used to having my y prime be in front and be positive, so I'm just going to multiply everything by -1, rearrange things. It doesn't matter because on the right side we have a 0. So this is just all going to be the same thing as y prime minus y minus lambda y is equal to 0. Did I lose anybody up to date? No. So now I'm just going to factor out a y from this. So I'm going to have y prime is equal, y prime minus y times 1 plus lambda is equal to 0. So I factored out a negative y from each of these terms. I was left with the 1 plus lambda is equal to 0. So now I have something that's close to this form again, where I have y prime, y, and then some coefficient. So again, I just go to my auxiliary equation, which is nice and easy because I don't even have a y double prime. So it's m minus 1 plus lambda is equal to 0. So my m is equal to 1 plus lambda. Therefore, my capital Y as a function of little y is equal to some constant times e to the 1 plus lambda y. That make sense? So now I have my capital X, I have my capital Y, and if I want to find my u, I can just multiply those two together. So I say c e to the negative lambda x times c e to the 1 plus lambda y. Constant times a constant is just another constant. E to the negative lambda x plus 1 plus lambda y. And that is your final answer for U. And that's pretty much everything that you're going to need to know about separation of variables with PDEs for this test.
What kind of variation is there onto that?
You mean like changing it up?
Yeah.
So they can put coefficients in front of here, so they might say like 2 there, and all that's going to do is throw a 2 there. Or they can make the right side something different. So like a lot of times the right side is just going to be a constant, so it'll be nice and easy. Whereas this time, since you had the function y over there, you had this 1, but a lot of times that won't even be there, so your y equation is going to look very similar to the x that you had here. But that's going to be the only differences that they can throw in there. This was worth 25 points on the test. So, yeah. No, I'm saying this is a nice easy 25 points to get. Everybody's good with this, I'm going to raise it. The only way that they'll ask you for this one is, like I said, they'll throw a coefficient in front of maybe one of these, or they'll change up what's on the right side, maybe make it a constant, something like that. But anything other than that, they're not going to get too tricky. That's pretty much it. Okay, now we're going to get into a nice, fun eigenvalues.
I guess this will be 25 points. We have an extra topic. Oh my gosh. Hey, Alva, smile.
This was the eigenvalue problem that I had on my test. I'm just going to, for the sake of time, I'm just going to go through this problem and explain each step along the way. And if you can understand this, then it's pretty much everything you're going to need to know about eigenvalues. There's one other thing that I can show you that isn't included in this question, but I'll explain that when I get to it. Okay. So this is what it gives us, and it says find all eigenvalues and eigenfunctions. So the very first thing that we have to do anytime we're given any eigenvalue is we need to figure out what m is equal to. So you have to do your auxiliary equation, find out what m is equal to, and it's going to end up being something where your lambda is going to be underneath the square root. So we have our auxiliary is going to be m squared plus this coefficient, lambda minus 3, times, we don't even need an m here, is equal to 0. So I know that my m squared is equal to, just subtracting this over to the side, it's going to be negative lambda minus 3, or you can just rewrite that as 3 minus lambda. Okay? So then therefore I know that my m, if I take the square root, my m is going to be equal to plus or minus square root of 3 minus lambda. So when you write that down on your paper, make sure you box it because you're going to have to come back to that for each of your 3 cases. So, now is where we get into our fun eigenvalue parts, our 3 cases. So, a lot of you guys might know, like, you take some, first of all, I do it slightly differently than the way that they teach it. The way that I do it, I think, makes more sense than the way they teach it. So if this way makes sense, you can rewatch the video. If you are a little unsure, email me, because I think this is a whole lot easier to understand than the way that they teach it. The whole purpose of eigenvalues is saying, I know that right now we have something underneath the radical that can change. If this thing that's underneath the radical is equal to 0, then my m's are just going to be, both of them are going to be 0. They're both going to be the same thing, and nothing's going to change. So in that case, my y, if my m's are both equal to 0 and they're both equal to the same thing, then I know that my y's are going to be one form of an answer. And in this case, it would be C1 plus x C2. You don't need to write this down. I'm just explaining. If you want to write it down, you can. I'm explaining like what the purpose of eigenvalues are. So if my m's are both the same thing, then my formula is going to be in that type of answer, where this is technically e to the m x times e to the mx. But since your m's are both 0, those would cancel out. Now, if I had this thing that's underneath the radical, if that whole thing ends up being a positive number, then my m's are going to be different numbers, and it's going to be m equals positive some irrational number, so some long decimal, whatever, and then I'm going to have minus that same long decimal, because if this is just a positive number, it's going to be the square root of that positive number, and I'm going to get something. And in that case, I'm going to have 2 distinct m1 and m2. And if I have 2 distinct roots that are m1 and m2, then my answer is y is equal to c1 e to the m1 x plus c2 e to the m2x. So this is another case that could be possible. The third thing that could be possible, first one it's 0, second one this is positive. The third case is it could be negative. Now if you have something, this whole term is negative, you have something that's negative underneath the radical, then you know you're going to be dealing with imaginary. And you're going to have your m is going to be equal to plus or minus I times something. And when you have an I in your roots, when you're solving for your m's, then you know your answer is going to be in the form of y equals e to the alpha c1 cosine of beta x plus c2 sine of beta x. So the reason why we're doing the 3 cases is because in this case we have the answer that's in one form. In this case we have the answer that's another form. And in this case we have the answer that's a third form. And we have to figure out which one of these works, which one of these can happen, which one of these gives us values that aren't just C1 and C2 are 0. Okay? So if this made sense to you, hopefully eigenfunctions and eigenvalues make sense. If it didn't make sense, just pay attention to everything else. As long as you know how to solve the problem, they don't care if you understand, sadly.
Why is it not C2 e to the minus m2x?
Here?
Yeah.
So, well, yeah, it would technically be minus m2. I'm just saying that your m2 would be a negative value, and your m1 would be, so this would be a negative value, that would be a positive value. But you'll see that when we get into the problem. But, yeah, this was just showing that this would be one of your exponents, this would be the other exponent. One would be positive, one would be negative. The key is that they're 2 different values. Okay. So, I'm going to erase this just to save space. Hopefully that made sense. If it didn't, like I said, ignore it. They don't care if you understand. They just want you to get the answer right. So, first case that we're going to start with is this is where I differ slightly from the way they do it. I'm going to take this whole thing that's underneath the radical, and I'm going to set that equal to what I want to do for each of my cases. So for my first case, I'm going to say that this is equal to 0. So if this is equal to 0, then I know that my m is equal to 0. And if my m is equal to 0, then I know that my y is going to be equal to c1e to the mx, which is just going to be 0x. So this is just going to go to 1. And then it's plus c2. Since both of my m's are the same, I have to multiply it by an x, e to the 0x. And again, this is just going to go away and be 1. So this y is just going to be c1 plus c2 times x. Okay? And now you go into plugging in your initial conditions. So I know that y of 0 is equal to 0. So if I plug in 0 here, I get c1 plus c2 times 0. That goes away. I have c1 is equal to 0. Okay? Now I take the derivative of this. So my y prime is going to be equal to derivative of constant is 0. Derivative of c2x is just going to be c2. And I know that no matter what I plug in for x, it's going to equal 0. So I just have 0 is equal to c2. So since both your c1 and your c2 are 0, you get no eigenvalues. So you have no eigenvalues for case 1. Yeah, sorry. Because I said that my 3 minus lambda is equal to 0, so I plug that into here, and I get plus or minus square root of 0. So my m is equal to 0.
Why is y prime?
I'll do the next part on this side. I'll try and move it out. So now, yeah.
The last step where you substitute in.
Yeah. So what I did was, you got to the point where it's y equals c1 plus c2x, right? I had my initial conditions up here. So y of 0 is equal to 0. So I plug in 0 for my y, 0 for my x, and all that I'm left with is 0 equals c1. Then I take the derivative, and all the derivative is y prime equals c2. And I know that my y prime of, no matter what, I don't even have an x in here, so it doesn't matter, is going to be equal to 0. So I have 0 is equal to c2, and that's where I get my c2. Okay? So this is your case 1 done. This is where you set it equal to 0. Now we're going to go case 2. And my case 2, we're going to say that everything underneath this radical is going to be positive. Because if it's positive, then we know we're going to get rational numbers, and they're not going to be imaginary. So we're going to have something, a different form of our answer. So if my 3 minus lambda is greater than 0. Now, this is where it differs from the way they teach it. The way this is simple for me is I'm going to take my 3 minus lambda, and I'm going to set it equal to alpha squared. Now, this is just a placeholder that's going to make for later steps easier. The reason why I can do this is because I'm saying that it's greater than 0. If I take any constant and square it, it's going to be positive. So by setting 3 minus lambda equal to this, I'm saying that it's a positive number. Okay? Because then what I can do is when I go to my m's, and I say that my m is equal to plus or minus the square root of 3 minus lambda, I can say that it's plus or minus the square root of alpha squared. And the square root of alpha squared is just alpha. So my m is just equal to plus or minus alpha. So now when I plug back into, when I go to find my y values, I have y is equal to c1 e to the alpha x plus c2 e to the negative alpha x. Okay? Does that make sense? So now I go to plug in my initial conditions, and I say y of 0 is equal to 0. So I say that 0 is equal to c1 e to the alpha times 0, that's just going to be 1. So I'm going to leave that off. And again, e to the negative alpha times 0 is just going to be 1 again. So I get 0 is equal to C1 plus C2. And that's what I get from my first initial condition. For my second condition, I got to take the derivative of this. So I'm going to say that y prime is equal to alpha C1 e to the alpha x minus alpha C2 e to the negative alpha x. That's just the derivative of that. Now I'm going to plug in this. So from this equation here, I get the relationship that C1 is equal to negative C2. Okay? So I plug that into here while plugging in my pi for x and 0 for y. So I get 0 is equal to alpha. C1 is equal to negative C2 e to the alpha times pi minus alpha C2 e to the negative alpha times pi. So this can get a little tricky trying to solve for, because ideally we want to try and solve for what C2 is. So what I'm going to do is I'm going to factor out a C2. So we have 0 is equal to C2 times, we get negative alpha e to the alpha pi, and we get minus alpha e to the minus alpha pi. So now we're at this point, and we say, okay, is there any way that this could possibly be 0? This factor right here. We know that e to any power can never be 0. And we said that alpha was, I didn't specify it, but your alpha cannot be equal to 0. Cannot be equal to 0, because if it was equal to 0, then we would have the same thing, same condition as there. So we know that alpha is some constant. So if your alpha can't be 0 and your e to some power can't be 0, that means this can never be 0, which means in order for this to be true, your C2 has to equal 0, which means your C1 equals 0, which means, again, we have no eigenvalues. Because that's the same thing that happened with our first condition. So here, we have no eigenvalues. Does that make sense? So those are the first two cases. The majority of the time, your first two cases are both going to come out to be nothing, and then the third case is where you're going to get to have your fun. So we get to the third case, which now our 3 minus lambda is going to be less than 0. And if you think about this, if the function that's underneath your radical is less than 0, that means we're going to end up having imaginary numbers. So what we're going to do, since over here we set it equal to positive alpha squared in order to be a positive number, we're going to take our 3 minus lambda and we're going to set it equal to negative alpha squared. Because we know that this is always going to be a negative number. Because alpha squared will always be positive. If you multiply it by a negative, it's always going to be negative. It's always going to be less than 0.
Do you always do that? Like you're always going to
I always do that.
Okay.
So if your m is like 1 plus or minus whatever, whatever you have underneath the radical is what you use. You set that equal to 0, you set that equal to positive alpha squared, and you set that equal to negative alpha squared. Whatever's underneath the radical.
Okay, thanks.
Okay? So we have this right here. Again, we plug this back into our m. So we have our m is equal to plus or minus the square root of now negative alpha squared, which is going to give us plus or minus I alpha. Okay? So these are now your m values. So you get, from there you get y is equal to, it's going to be e to the coefficient here, which is just 0. So I'm going to leave that off because that's just going to be 1. Times C1 cosine of this number here. the number that's being multiplied by your I. So alpha x plus C2 sine of alpha x. Okay? So now that we have our y function, we can plug in our initial conditions again. So we plug in 0. We have 0 is equal to C1 cosine, any alpha times 0 is 0, plus C2 sine of 0. We know sine of 0 is going to be 0, so that whole term goes away. We know cosine of 0 is 1, so we have 0 equals C1. For the derivative, I'm going to erase this part of case 2, just so that way everyone can see this next part. It's the important part.
But alpha itself isn't 0,
Okay, so now we take the derivative, and the derivative is going to be y is equal to negative alpha C1 sine of alpha x plus alpha C2 cosine of alpha x. But I know that my C1 is equal to 0, so I'm going to disregard that entire first term. So I plug in my C1 is equal to 0. So I can just say that my y prime is equal to alpha C2 cosine of alpha x. Now I plug in my second condition and I say that 0 is equal to alpha C2 cosine of alpha pi. So we need to figure out how can this right side possibly be 0. We know that alpha can never be 0 because we said it cannot, that's what we defined it as, it cannot be equal to 0. We don't want C2 to be equal to 0 because then we have C1 and C2 are both equal to 0 and we have no solutions, no eigenvalues for the entire problem. And that's not going to happen. So we know that this cosine of alpha pi has to be equal to 0. So in order for cosine of something to be equal to 0, this something, if you think about the unit circle, this alpha pi is going to need to be equal to, if you think about the unit circle here, your cosine is 0 up here and down here. So this is going to be at 1/2 or half pi, pi over 2, or 3 pi over 2, or 5 pi over 2, or 7 pi over 2, or any odd number times pi over 2. So this is where we're going to start representing that with n's. So the way that we can represent any odd number is 2n minus 1 over 2 times pi, where n is equal to 1, 2, 3, 4, and so on. Okay? So these pi's can divide out. The pi's are going to go away on either side. And we know that our alpha is going to be equal to 2n, or 2n minus 1 over 2. So this is going to be important because we're going to plug that back in later. But this isn't my eigenvalue. My eigenvalue is what lambda is equal to. And I know that my 3 minus lambda is equal to negative alpha squared. So what I'm going to do is I'm going to turn this into negative alpha squared, so that way I can set it equal to my 3 minus lambda. So the first thing I'm going to do is I'm going to square this, so I square the right side, and then I throw a negative in front of it, and throw a negative in front of that. So all I did was made the left side negative alpha squared, and the right side I just did the same things to. Because now this negative alpha squared, I can change it to my 3 minus lambda is equal to negative 2n minus 1 over 2 squared. Since I want to find what my lambda is, I'm going to add lambda to this side, bring this over here, and you get lambda is equal to 2n minus 1 over 2 squared plus 3 for n equals 1, 2, 3 forever. And those are your eigenfunctions, or eigenvalues, sorry.
Which one?
So that's the answer to find all your eigenvalues. Now, in order to find our eigenfunctions, all we do, it's a nice and easy last step, we come back over here to where we first defined our y, and we have to plug in these eigenvalues. But it's nice and easy because we knew that our alpha is just equal to 2n minus 1 over 2, right? That's what we found out here before we changed everything around. So we can just take this, plug it in for our alphas here. We know that c1 is equal to 0, so that term goes away, and all we're left with is y is equal to this c2, I'm just changing to cn, sine of 2n minus 1 over 2 times x, for n is equal to 1, 2, 3, dot, dot, dot. This n equals 1, 2, 3 is important because they're going to probably take up the point if you don't have it. And that's your final answer. This is your eigenfunction. These are your eigenvalues. And that's the whole problem.
Are those both y primes?
Now this problem was also worth 25 points, which was the same thing as the separation of variables, which was much simpler, but that's the way that they decided to separate.
Right here. I don't understand.
Any questions?
Is that even a y prime? I don't think, okay, is that, are they both y primes? I just
Yeah.
It is so how does y prime?
How they get C1 and C2?
I understand that they get y prime.
Want to try it to not make it happen. But if you have to, then you have to. But since you found a way to make it basically equal to 0 without making it equal to 0,
No, what he did was it was plus, and then he said, well, that equals to 0, so he put it as an equal. I got confused. He did it for us.
Okay, does anybody have any other questions on anything, eigenvalues,
Oh no, that's what he
stuff like
said.
that? If not, I'm going to do like 5 minutes on Fourier series because it's only going to be on there for a little bit. I'm not even sure, like I know the professors are saying it's going to be on there. We haven't had it, they haven't had it on the third test at any point in the past. So I'm still skeptical about it. I think it's going to be the spring problem all over again, where they tell you it's on and it's not there. But I'll go over just the basics, formulas, stuff like that, and then I'll let you guys get going because I know it's been for a while. Okay, guys, we're in the home stretch now. A couple more minutes. Bear with me. Only a couple more minutes in this crowded, tight, hot room. So, Fourier series. Basically, what it is, it's going to be involved with boundary value problems. And basically, if you have some function that's defined on one segment, so from negative L to L, from 0 to L, something like that. So for a set region of space. So we have a function. Let's say the function's just nice and simple. We'll just take this function right here, where this is L, and this is negative L. And this is our f of x. So one thing that they're going to ask you to do is they're going to ask you to expand, or they might, I don't know how they're going to ask the questions because they haven't had it ever on the third test. But one thing they might ask you to do is draw out the sine function, the sine Fourier series for the interval from negative 3L to L, or to 3L, sorry. So if it gives you that this is the function. So basically, all you're going to be doing is you're going to be repeating this function, the same interval, you're just going to be copying it over and copying it over. Actually, sorry, so it gives you this as the function, just from 0 to L. Sorry if you already wrote that down. So the thing that you need to know about the sine Fourier series is it reflected about the origin. So if we were to extend this series, or this function, over the portion 0 to L, if we were to extend it over this whole interval, we want to reflect it over the origin, which means it's going to continue down this way. Okay? Then when you get to this point negative L, we're just going to keep repeating the same sections. This goes a total distance of 2L, so we're going to repeat the same section from negative L to negative 3L. So it's going to be at the same height up here. It's going to cross at 0, and it's going to go down to at the bottom at negative 3L. And then you're going to do the same thing on the right side, starting here, going up, like that. So that's what it's going to look, that is your sine series. If it asked to draw out the visual representation of the sine Fourier series over that interval. So all it's saying is this function is going to be repeating, and it's going to be reflected about the origin. The way that this would be different if they asked for cosine, I'm going to go to brown, see if this works. So your brown, that's not So if it's asking for your cosine, the only way that that's going to change is your cosine is reflected about the y-axis. So instead of going down, it's going to reflect over the y-axis, so it's going to look like this. And then it's just going to repeat this, the same interval, the same way that your sine repeated. So it's just going to come down and up. And then here it's just going to come down and up. So here the red is your cosine and the purple is your sine, where this is the given function. Okay? And if it asks you to represent the series like as a formula, write out the f of x. This is going to be the way, these are the formulas that I'm not sure if they're going to give to you or if you have to memorize. You're probably going to have to memorize just in case. But these are the formulas that you need in order to solve for what the Fourier series is actually going to be. So this is the total general Fourier series where you have your a sub 0, your a sub n, your b sub n. And in order to find your a sub 0, it's 1 over L, the integral from negative L to L. Your b sub n is going to be the same, or your a sub n, sorry, it's the same thing, but then you multiply it by cosine of n pi x over L, and your b sub n is that. I guess that's good.